We have a plutonium problem. This is Dragonfly, NASA's flying rover designed to explore Titan, the icy moon of Saturn, 1.5 billion kilometers away from Earth. And it will do it while being powered by the final few kilograms of a nuclear fuel currently left in the United States stockpile. Tucked inside this drone, nestled between thermocouples, there is a small 4.8 kilogram chunk of a man-made isotope, plutonium-238. And the United States is running out of this vital material. And the shortage has already affected NASA missions, like the Europa Clipper's mission to Jupiter's moon, where it will need to get by with the power provided to it with its solar panels, which will receive extremely low intensity light in the distant reaches of our solar system. Many at JPL believed Europa Clipper should have been powered by plutonium-238, but with the material in short supply, it was saved for missions like Dragonfly. This isn't good, it's quite bad actually. We really need more plutonium-38 to do cool science stuff. So, what are we going to do about it? This hasn't always been a problem. Some positive things did come out of the world's relentless race to expand nuclear weapon arsenals during the Cold War. Like this, and even this. Deep within secretive processing facilities around the world in the 1950s, scientists began producing fissile plutonium-239 in vast quantities. The United States, Russia, United Kingdom, France, China, and Israel all developed nuclear weapons during this time. And in the process of refining and extracting weapons-grade plutonium, other isotopes emerged, useless for warheads and discarded as waste. Or so it seemed. NASA saw something different. What the military considered a byproduct, they saw as an opportunity. Among the leftovers were the ingredients to make plutonium-238, an isotope unlike its bomb-making counterpart. It doesn't sustain a chain reaction, but instead, it emits a steady, reliable heat. This isotope could be harnessed as a safe lifeline for spacecraft venturing into the darkest, coldest corners of the solar system. The only way to create this element is to bombard other elements with neutrons in a nuclear reactor. This isotope is differentiated from the one that leveled Nagasaki by just a single neutron. This single neutron difference changes plutonium from one of the most tightly controlled substances in the world to this. This wonderful material glows red hot. Not for hours, not for days, not for weeks or months or years, but decades. A slow, consistent radiation of heat that halves every 88 years. And this heat can be used to generate electricity, but more on that later. Since its discovery as a power source, plutonium-238 has been vital to NASA's missions. First used in the Apollo lunar surface experiments, it later powered the Voyager probes, which are still transmitting from interstellar space. Cassini explored Saturn with its help. The Curiosity and Perseverance rovers roamed Mars with its heat. And now, Dragonfly will rely on it to explore Saturn's moon, Titan, keeping its instruments running in the extreme cold and providing the energy needed for powered flight on another planet's moon. So, why are we running out of this wonderful material? In 1988, with aging reactors and a nuclear weapons stockpile so large they could end the world instantly, the United States halted its production of weapons-grade plutonium. I think we can all agree this was a good thing, but this decision has hindered deep space exploration. With the shutting down of the K reactor in the Savannah River site, the US lost its ability to produce plutonium-238, forcing NASA to ration a dwindling supply of the valuable material. This problem became even worse when in 2010, the US stopped importing the isotope from Russia. So, a decade ago, NASA and the Department of Energy restarted its complex production. But with current production at just 550 grams per year, supply is not keeping pace with demand. So, what is NASA doing to address this problem? There are some alternatives if plutonium refining does not increase to meet demand. The first thermal generator tested by NASA in 1959 used polonium-210 as its nuclear source. A single gram of polonium-210 generates 140 watts of power. However, its short half-life means its power output halves in just 138 days. The fastest ever journey to Mars took about the same time. During that time, the spacecraft would have to radiate that heat generated by the fuel to space. Losing half your power before you've even arrived isn't ideal, ruling it out of most space missions. The unique demands of space exploration gave rise to 3 primary engineering requirements for a nuclear fuel suitable for spacecraft. The first requirement is that the fuel must last long enough to power a mission without sacrificing energy density. This means the isotope's half-life should be between 15 and 100 years. Out of nearly 2,900 radioisotopes, this criterion reduces the options to just 22. Next, the fuel must only emit radiation that is easy to shield, ensuring the protection of both the spacecraft's sensitive instruments and any personnel handling it during preparation. This means of alpha, beta, and gamma particles, we want the material to only emit alpha particles, which generate more heat and are easily blocked. The alpha particles emitted by plutonium-238 are essentially helium nuclei traveling at 15% the speed of light and carrying 5 mega-electron volts of energy. As they collide with electrons and nuclei within the fuel, they release their energy as heat. But if emitted near the pellet's edge, the alpha particles are easily stopped by light materials. But it's not the only alpha emitter. Take curium-244. Its half-life of 18 years is a little short, but still within the acceptable range. Curium-244 was initially considered as a potential substitute due to its high power density, which is 5 times greater than that of plutonium-238, and it has a stable high-temperature oxide fuel form. But its higher gamma and neutron emissions, resulting from its higher rate of spontaneous fission, significantly increases the need for heavy shielding to protect both handlers and spacecraft equipment. Plus, producing curium-244 is far more difficult. The best way to create it is for plutonium-239 to capture successive neutrons and for it to decay into curium. This is expensive and impractical, so there is currently no infrastructure to produce it in the large quantities needed for space missions. Stability under extreme conditions is equally critical. The fuel has to withstand launch accidents and atmospheric re-entry. We don't use completely pure plutonium-238 in spacecraft. Instead, they rely on plutonium oxide pellets, which are encased in iridium shells to contain the material safely. Iridium was chosen because of its high temperature material properties, being strong and ductile even at 1000 degrees Celsius, allowing it to safely deform and contain the radioactive pellets in the event of an accident. In 1967, a plutonium generator was recovered from the Pacific Ocean after a failed launch of a weather satellite. Its plutonium-238 was reprocessed and successfully used in another mission. Similarly, during the Apollo 13 mission, the lunar module's generator sank intact to the ocean floor, where it remains safely contained, keeping some local fish warm. Finally, the fuel must be cost-effective and producible in sufficient quantities, using existing infrastructure like nuclear reactors. Gadolinium-148 is another great option, with a long half-life of 75 years with only alpha decay mechanisms. But the only way to produce it is to bombard targets with very high energy protons, requiring very expensive particle accelerators. So, to produce it in enough quantities, a much larger investment is needed. So, in short, plutonium-238 is just a miracle material that is perfect for space exploration. NASA has 2 options to tackle this supply and demand imbalance: either increase production or figure out a way to use current supplies more effectively. The current method of extracting electricity relies on the Seebeck effect. The Seebeck effect essentially allows us to generate an electric current through a heat differential, as charge carriers, both electrons and electron holes, will move from hot to cold. So, if we have 2 semiconductors, one with charge carriers in the form of electrons and one with charge carriers in the form of holes, a potential difference between the 2 semiconductors will form when a heat gradient is applied. This potential difference causes a current to flow in the external circuit. These 2 semiconductors need to be both thermally insulating to ensure this heat gradient is maximized, but also electrically conductive to maximize the current. These two material properties are typically linked. Copper is both a great electric and heat conductor, while iron is a poor electric and heat conductor. Having a single material that is a great electric conductor and a poor heat conductor is extremely rare. For this reason, two unique materials are used for the P and N-type semiconductors: lead telluride for the N-type and an alloy commonly called tags for the P-type, which is formed from tellurium, silver, germanium, and antimony. NASA has explored more efficient ways to generate electricity with the heat plutonium-238 provides, including the use of the Stirling cycle. This cycle operates by alternating compressing and expanding a gas in a sealed system, allowing heat to be converted into mechanical energy, which then drives a generator to produce electricity. NASA focused its efforts on developing an advanced Stirling engine, a highly efficient system designed to work in the vacuum of space and be able to survive the harsh vibrational forces of the launch. Traditional radioisotope thermoelectric generators only convert heat to electricity at an efficiency of only 6 to 7%. Stirling engines can achieve efficiencies of up to 30%. This would more than quarter the quantity of plutonium needed for these space missions. Unfortunately, in 2013, after a decade of development, NASA cancelled the Advanced Stirling Radioisotope Generator project due to technical issues with the piston, underestimated costs and schedules, and budget constraints. So, increasing production is the only option left. Production restarted in 2015, and while initial production was just 50 grams per year, to date the production level is 550 grams, with plans to raise that to 1.5 kilograms per year. The current production entails 3 different facilities in 3 different states. During the Cold War, the Savannah River site separated and produced 400 kilograms of neptunium. Its long half-life means it's still usable as a target even to this day. All of the plutonium in the future lunar landers and the Dragonfly mission will be made from neptunium made decades ago stored in a site in Indiana. The neptunium, as a solution, gets transferred to the Oak Ridge National Laboratory. There, they distill the solution and precipitate the neptunium to create a metallic powder. This material is then carefully pressed into pellets and then encapsulated in aluminium to prepare it for irradiation. The encapsulation ensures the neptunium remains contained during its transformation in the reactor, maintaining safety and preventing contamination. Next, the encapsulated neptunium is placed inside a nuclear reactor, where it undergoes irradiation. Inside the reactor, the neptunium-237 nuclei absorbs neutrons to form neptunium-238. This isotope is highly unstable and quickly decays into plutonium-238 through beta decay. The reactor's neutron flux and duration of irradiation are carefully controlled to optimize the conversion rate and ensure the production of high-quality plutonium-238. After irradiation, the targets containing plutonium-238 are removed from the reactor and processed to extract the newly formed plutonium. This involves dissolving the irradiated material in acid and using chemical techniques to separate plutonium-238 from any residual neptunium-237 and other byproducts. The extracted plutonium-238 is then purified further to meet the rigorous standards required for use in space missions. Finally, it's converted into a ceramic oxide form, which is stable and suitable for use in radioisotope power systems and sent to the Los Alamos lab in New Mexico to be formed into the final pellets and placed inside the thermal generator. In 2011, when the Department of Energy started up the process, none of these facilities were ready for large-scale operation. They needed $90 million for modifications to existing facilities. All of this is simple in theory, and the overall process has been known since the Cold War, so why has it been so hard to build up the stockpile? Engineers and researchers are fighting a losing battle against unstable elements that are impossible to see. It's easy to write the diagram where neptunium simply turns into the right kind of plutonium by absorbing a neutron. But in reality, this is a statistical process. In the hot, messy, and energetic environment of the target, anything can happen. Neptunium might absorb one neutron and then split. Ideally, it absorbs a neutron and becomes neptunium-238, but once formed, this neptunium is also exposed to the same neutron bombardment. This is actually the main way neptunium-238 decays. 85% of the Neptunium-238 that is created is destroyed by neutron-triggered fission. Then, in the off chance that everything goes well and the Plutonium-238 starts to build up in the target, it is still being irradiated too, creating even more undesired isotopes. We need 85% pure Plutonium-238, and trying to separate two isotopes that differ in mass by 1 or 2 neutrons is almost impossible. These interactions are incredibly difficult to control. During one cycle, 1 gram of neptunium would yield just 0.5 grams of plutonium. To maximize the likelihood of Plutonium-238 forming, we want to expose the target to a stream of very concentrated neutrons for a short time in cycles. In between the cycles, the target is allowed to cool, while unwanted byproducts decay further. There are very few facilities capable of doing this, just 2. The high-flux isotope reactor at the Oak Ridge National Laboratory and the Advanced Test Reactor at the Idaho National Laboratory. And there is huge demand for these reactors. Nuclear physicists depend on these slots being available to study different isotopes, so the lack of places to irradiate the targets in addition to the low yield means the number game is not in our favour to build up the stockpile. So where do we go from here? The production process is slow and complex. The Oak Ridge National Laboratory is on track to produce 1.5 kilograms of Plutonium-238 per year. The Dragonfly mission alone will need around 4.8 kilograms, taking 3 years to produce. So we desperately need to increase supply because there are many more exciting missions that could use this incredible material if it was available. The success of the restart of US plutonium production has sparked interest in other space organizations. The ESA is well positioned to create their own manufacturing plant. France, having a large nuclear power base already, has a full facility meant to extract plutonium and uranium from spent nuclear fuels in La Hague. Looking to the near future, the possibility of using Plutonium-238 for lunar missions is gaining attention. While the moon offers better conditions for solar power compared to deep space, certain lunar regions such as permanently shadowed craters at the poles require alternate power sources. These regions are of high scientific interest, as they may contain water ice and other valuable resources. A steady Plutonium-238 supply could enable extended exploration of these areas, powering landers, rovers, and even infrastructure like communication relays or habitat systems during the long lunar nights. Ultimately, there is only one answer to this problem. Scaling up Plutonium-238 production to support both lunar and deep space missions is going to require a lot of money. And do you know what else requires a lot of money? These videos. This is the very first video I ever made. It was basically free to make. I taught myself how to animate over the course of a long weekend and made this video. It's pretty crap by today's standards. You can see all the vector graphics I created getting pixelated because my settings were wrong. That's something the comment section taught me how to do. Over the course of 9 years, this channel has gotten more and more popular, and I have constantly reinvested money into improving its production quality. I worked with Mike, our now head of animation, for the first time on this video, and our animations immediately got better. We hired Stephanie as a producer around 6 years ago, who worked on Real Engineering before branching out to start Real Science. We hired a full-time editor around then, along with a full-time animator for Real Science. Then COVID hit, and we hired a bunch more animators and producers and audio editors. Once we could travel again, we began hiring camera crews and spending more money on travel expenses. We have gone from making cheap 2-minute videos to making 20 to 30-minute long documentaries 3 to 4 times a month. We continue to upload the vast majority of our work for our audience to view for free here on YouTube. And we want to keep it that way. We do get help from our audience that have the means to do so, but I'd rather give you something of value in return for your support. That's why Nebula exists. You can directly financially support this channel while getting access to new and exclusive content from not just me, but loads of your favorite creators. On Nebula, we upload exclusive extra cuts from our videos. That's what this little plus symbol means. You can go to your library page and sort by plus. And here's all of the plus content from Real Engineering and our sister channel, Real Science. Hours of additional interview segments and documentaries that didn't quite fit into the niche of engineering here on YouTube. You can also sort by originals, which are high-budget original programming funded entirely by Nebula with your support. And here, there are even more documentaries made by us that are exclusive to Nebula. Logistics of D-Day, the Battle of Britain, and Real Science's Becoming Human series. And we've plans for even more original series this year. This is what Nebula is about, and 2025 is set to be Nebula's biggest budget year ever, with even more money being funneled into original programming. So, if you want to watch all of that and watch my videos ad-free on Nebula, you can get 40% off the year plan at just $3 a month. And what's even cooler, if you like it and want to share it with your friends and family, once a month, subscribers can share guest passes that provide 1 week of free access to Nebula, and they don't even need to provide any payment method, because we want to build a business you want to support, not one you forget you are supporting. So, if you want to check out all the fascinating exclusive content on Nebula, go to nebula.tv/real engineering or click the link in the description to get 40% off our yearly subscription today for the incredibly low price of $3 a month.